Okay, now we're asked first to find the speed after one cycle of the pendulum, given the information we have here. The information being that the ball starts from rest, and every cycle it increases in speed by 1.6 nominal lengths per cycle. Okay, so speed after the first cycle, what is it? And you should really think through this if you haven't, using this fact. Well, we started at 0, okay? And you should be thinking through this. Pause and think through. We started at 0 and changed at 1.6 nominal lengths per cycle. That means every cycle our speed increased by 1.6 nominal lengths per cycle. So after one cycle, it's going to be going 1.6 nominal lengths per cycle. It started from rest, so the speed is 1.6 nominal lengths per cycle. The change in speed is 1.6 nominal lengths per cycle. Started from 0, so that will be its speed. The change in speed will be the speed. Okay? Now, how do we get the change in its position? Because what we're asked next is to find through how many nominal lengths will it have rolled by the end of that first cycle. Okay? Well, change in position is equal to the average velocity multiplied by the change in clock time. Going back to our basic relationship, we know its speed or velocity, okay? We want to find the change in its position. Well, but we need the average velocity, and right here we just have the velocity. So we need to find the average velocity, and having found that, multiplying by the change in clock time will give us the position by the simple algebra of multiplying both sides by the change in clock time here. So delta S is V average times delta T equals what? Well, we have to find V average. But for this interval, okay, what's delta T? It's one cycle. And we know that the initial velocity in the interval is 0 nominal lengths per cycle, not per second. And the final velocity is 1.6 nominal lengths per cycle. Well, if we know the initial and the final velocity on the interval, and we know that the V versus T is a straight line, then we know that the average velocity is obtained by adding the initial and the final and dividing by 2. In other words, just averaging the initial and the final. Having done that, well, I'm kind of out of space here, but we add the 0 nominal length per cycle to the 1.6 nominal lengths per cycle, divide by 2. You can figure out what that is, but I'm going to move this over a little bit. And bring this in. And we can see how this develops, okay? So, the 0 nominal length per cycle plus 1.6 nominal length per cycle initial plus final velocity divided by 2 gives us the average velocity. Okay, so during the first cycle, initial is 0 nominal lengths per cycle, final is 1.6 nominal lengths per cycle, so the average is 0 nominal lengths per cycle plus 1.6 nominal lengths per cycle divided by 2, which gives you 0.8 nominal lengths per cycle. Thus, your displacement being the average times delta T is going to be the average velocity, 0.8 nominal lengths per cycle, multiplied by delta T, which is one cycle. And that does give you just 0.8 nominal lengths because this cycle's in the numerator, this cycle's in the denominator. Okay? So we go 0.8 nominal lengths during the first cycle. And so this is our position after the first cycle. Now, during the first 2 cycles, how far does it move? Okay? Starting from rest again. We could analyze this by analyzing just what happens during the second cycle and adding the change in position to what we got during the first. But it's going to be simpler at this point to kind of go in terms of what we did here. The process will be exactly the same, and we'll worry about the other later. Okay, so using the same reasoning throughout. Okay, first of all, during the first 2 cycles. The first thing we calculated was the speed at the end of the first cycle. Okay? Now we got to figure the speed at the end of 2 cycles. How do we reason that out? You should pause and do that yourself rather than waiting for me to tell you, or rather than allowing me to tell you before you figured it out. Well, at the rate of 1.6 domino lengths per cycle, in 2 cycles, the velocity will change by 3.2 domino lengths per cycle during this 2-cycle interval. So for this interval, your initial velocity would be 0 domino lengths per cycle. Final would be 3.2 domino lengths per cycle. Now you want to find out how far we move during the cycle. You find the average velocity. Knowing you know the initial and the final, you can find the average. That's going to be 0 domino lengths per cycle plus your final 3.2 domino lengths per cycle divided by 2 gives you an average of 1.6 domino lengths per cycle. So delta S is average velocity times delta T. What's average velocity? 1.6 domino lengths per cycle. What's your delta T? It's 2 cycles, since this interval starts at the beginning and goes through 2 cycles. So we multiply the average 1.6 domino lengths per cycle by the 2 cycles, and we get 3.2 domino lengths. Now, it's worth noting that this is 4 times the distance we traveled on the first. Okay? So the distance after 2 cycles is 4 times the distance after 1 cycle. And that's consistent with Galileo's experiment, which you might want to look up, but it's very consistent with what we obtained last time by a slightly more abstract reasoning process. Okay, this is very concrete. Now you should finish this problem. Okay, that's part of your assignment, to finish the problem, which asks you to calculate the positions at the end of the 3rd and the 4th cycles. Of course, we know at the end of the 5th cycle, you will have traveled the entire 20 domino lengths. It wouldn't hurt to use this reasoning, though, to confirm that, give you a little bit more certainty in the process that you're using to reason it out.